Let's go over limit laws and 1.4, which will be calculating limits. I don't have slides, so I'm doing this based off the notes I had written down in class today. So, um, so first let's assume two postulates. The limit as x approaches a of f of x and limit as x approaches a of g of x will be defined. So we're just going to assume they're defined. It's So both of these are defined, and we'll use these for limits. So I'm not gonna go into detail on how they work or how they were derived or anything, because that's like what I like to do in my videos, but I won't do it here because simply it'll take forever. So the first limit law is that the sum of the limits, or the sum of the limit of the sum of the functions will be the same as the sum of the limits. So be limit as x approaches a of f of x plus limit as x approaches a of g of x. Self-explanatory. I'm not going to explain too much on that. Same thing for differences. I wish I could just copy and paste, but I can't. Will equal this, but just with a minus. So limit as x approaches a of f of x minus limit as x approaches a of g of x. So it's quite sloppy, but those are the basic limit laws. There's just like 10 more. So for 3, it's the constant multiple rule, I think. Well, that's what they call for derivatives, but here we're the thing. So it's the same thing as we can just pull the constant out. And these are all pretty self-explanatory if you can think of it like direct substitution. But I'm not going to get into any of that right now. And limit as x approaches a of f of x times g of x, or the product of those two, will be the same as, guess what? The limit of one times the limit of the other. I mean, this is like, you don't even have to memorize this. I mean, this is like pretty easy. That's the fourth rule. The fifth rule is the difference quotient. But here, make sure that the limit of f of x is not 0, or g of x is not 0. Because that will be indeterminate or does not exist. So make sure that. I mean, you can use algebraic manipulation, which we'll get to a little bit later. But I'm just trying to hurry up because I don't have time. We have the power rule. It's not the derivative power rule. It's just this. So I think it's f of x to the power n is the same as limit x approaches a of f of x times n. So, I mean, to explain this in English, the limit of x approaches a of a function to the nth power is the same thing as the limit to the nth power. This should be pretty easy. The limit of a constant is just a constant because nothing changes. The variable doesn't lead to a net change. The limit of x approaches a of x would just always be a. And that's just, I mean, it's a polynomial function, which we'll get to a little bit later. But, I mean, they define that one, although they literally cover it later. Limit as x approaches a of x of n equals a of n. And this is a little bit tricky because you have to make sure n is not a negative integer. Because what if its limit as x approaches 0 of x of negative 1? Then it would be 0 of negative 1, which is undefined. So I guess the book doesn't really, my book doesn't really go into it, which is by James Stewart, I think. But n can't be negative. Or n could be negative. So it's if n is negative, then this doesn't apply for x equals, or for the a equals 0. But if n is a negative, then it works for everything. And again, these are just simple limit laws. I'm sure you could look these all up, but I'll be going over them. Equals n over a. So limit is n over a. Okay, great. Now we're done with that. Now let's evaluate the following limits. So we'll do 2x cubed minus 3x plus 4. I don't have a calculator, so maybe my math might be a little bit slow. We'll do 5. So here we could just direct substitution it because this function is continuous, meaning that if we looked on a graph, I don't know how it will look like. I mean, I guess it's cubic, so it probably looks something like this. But notice that on every point, each point has both sides approaching the same point. So that leads to the derivation of the rational expression. But this would just be 39. And yeah, the limit is 39. Self-explanatory. And we use the laws 1, 2, 3, 7, 8, 9. You can go back, but I'm not going to explain that. Now we're going to go over this one, which is the limit as x approaches negative 2 of x cubed plus 2x squared minus 1. I mean, the thing that immediately comes to mind here will be direct substitution using the quotient law. So we'll break this into two functions. So the limit as x approaches negative 2 of the top part, and then that of 5 minus 3x. Let me do the math in my head. That would be 11, and that would be 1. So 1 over 11 is the limit. So this leads us to our direct substitution method. And I'm just going to write it out because I don't want to, type it out because I'm fast at typing. The direct substitution method states that for polynomial or rational expression, you can just plug a or what x is approaching. And I'm doing this using kind of my own words, so this might not be the formal definition, or what x is approaching into the function, or just evaluate f of a, and that will be your limit. Note that for rational expressions, again, the denominator can't be 0. This works for trig functions. So the limit as theta approaches 0 of cosine theta is equal to pi. Cosine theta is equal to pi. So simple stuff. This is the factor method, which is just used for algebraic manipulation. It's pretty easy. So the limit as x approaches 1 of x squared minus 1 x minus 1. So again, we can't just plug this in using direct substitution because the thing is undefined. But remember, this is a difference of squares. And we can just simply use algebraic manipulation. The reason we can do so is because this function is the same exact function as this one, except for the fact that this is undefined. Because so like for every other point, these ones cancel out, but at 0, it's undefined. But remember, a limit isn't finding what a function is at a point. It's finding what it's approaching. So we just use direct substitution, and that equals 2. Sorry, my throat kind of hurts. But it would be indeterminate if we did it in here because 1 minus 1 over 1 minus 1 doesn't work. So next example. If f of x equals g of x, and that was kind of derived from the last one, when x isn't equal to a, then the limits are the same, basically. And I hate writing this. Like, it's just... So remember in the last one, that was x plus 1 is the same thing as x minus 1, x plus 1 over x minus 1, except for when a is equal to 1. So on the graph, it will look like this. This will look like the undefined graph, but the other point will look like this. But note that the limits are the exact same, because they're still approaching the same point, regardless of whether that point is defined, which is what a limit is. So, next thing, for piecewise, I guess these are all simple. Another definition that we have to use, or theorem, is that a limit as x approaches a is only L if limit as x approaches a equals L and limit as x approaches a from the left side is equal to L. I mentioned that like 10 times over, so it doesn't really matter. I'm going to skip these examples because they're common sense. And now squeeze theorem. So a function that is greater than a function. What does that mean? So I asked my teacher this today because, 2x is greater than x on the intervals of x is approaching infinity, or 0 to infinity. But down here, we'll see that this function actually takes dominance. So there's certain functions that we'll go over, but typically it'll be trigonometric when we use the squeeze theorem. So like x squared is always greater than x, or absolute value x. If you look at it on a graph, it looks like this, and a thing won't look like that. So no matter what your input is of g of x, if this is g of x, and that is equal to f of x, g of x will always be greater. So, but the squeeze theorem, that's the dominance theorem. So if f of x is less than g of x, then limit as x approaches a of f of x is less than or equal to limit as x approaches a of g of x. I'm wasting numbers on this. The squeeze theorem is quite similar. So let's take this graph here, and we'll do this, and then we'll do this, and we'll do this. Let's say this is f of x, h of x, and g of x. That means f of x is less than g of x, and or equal to, and h of x. So note that if the limit as x approaches, so the first rule of squeeze theorem is that it must be defined, or this inequality must hold true when x is in an interval of a. So like right here, we see that it holds true because this is less than g of x, and h of x is greater than g of x, and f of x is less than g of x. So this theorem states that if the limit of x approaches a of f of x equals L, and the limit as x approaches a of h of x equals L, then the limit of x approaches a of g of x must also be L because it's somewhere squeezed in between. This is also called the pinching theorem or the sandwich theorem, but this will be used for trigonometric identities. So for example, let's say we want to evaluate the limit as x approaches 0 of x squared sine 1 over x. How would we do so? Well, this looks quite complicated, right? But if we wrote this out, remember that the range of the sine function is between 1 and -1. If we times x squared, this inequality still holds true because this is just basically a constant kind of between these three things. The limit as x approaches 0 of x squared is 0. Limit as x approaches 0 of x squared is also 0. So technically the limit would be 0 x squared sine 1 over x, and x squared sine over 1 over sine 1 over x is in the middle. So the squeeze theorem proves that the limit of that is actually 0 as well. One more thing we need to note is the important identity. Limit x approaches 0 of sine theta over theta, or sine x over x, which is equal to 1. Know this. You can prove it using L'Hopital's or some other squeeze theorem proof, I think, but we won't worry on that. And also this holds true even if theta is equal to 7x or 10x, which means that 7x over 7x equals 1, because you can just substitute 7x as theta here. So let's take a function, sine 7x over 4x, and I'm just going to do this by myself, so no book here, just to show you how easy it is. So we'll multiply it by a factor of 7x over 7x, which is just the same thing as 1. We haven't changed anything. 7x, and then we'll just multiply that there, or as the other denominator. This is the same thing as 7 over 4. And then remember, the limit as x approaches 0 of that is 1. So the limit is 7 over 4ths. So yeah, quick and easy math. Simple. I hope it's simple because I get it. But whatever. Limit as x approaches 0 of cosine theta minus 1 over theta. Again, algebraic manipulation. I would do difference of squares. Or conjugate pairs, that's what it's called. That would be cosine squared theta minus 1 squared over theta cosine. Oh, sorry, this would be theta squared, actually, is what the book says. Cosine 1. And remember, that's the same thing as negative 1 minus cosine squared theta. This is a trigonometric identity. Squared theta cosine theta plus 1. I'm tired. Sorry. That's the same thing as sine squared theta, negative sine squared theta over squared theta cosine theta plus 1. We can break this up into sine theta. We could break this up into negative sine theta over theta times sine theta over theta times 1 over cosine theta plus 1. Direct sub it in. That would be negative 1 plus 1. Or sorry, negative 1 times 1, because it's a product. And then times the last one, which would be 1 over 2. So that would equal... Wait. Sorry. Oh my gosh. I did it actually wrong, but I guess that's fine. Same thing, 1 over half. I used a different example than my book, but I did it anyway, so that's it for 1.4, which is, I think it's called calculating limit laws. Let me read it again. And I'm tired, so 1.4 calculating limits.